How do you determine whether an integral is going to be positive, negative, or zero? There are a few obvious cases, and then there are cases where it's harder to figure out. But let's start with the obvious ones. If the function is greater than 0 for all points xy in the region R over which we're computing the integral, then we're integrating a positive number being multiplied by little infinitesimal positive areas, and when we add them all up, we get a positive integral. So the integral of R of f of x comma y dA is greater than 0. A common example of that would be the integral over any region of dA. So in this case, f of x comma y is equal to 1, which is certainly positive everywhere. And this integral is actually just the area of the region R. So this integral is always going to be positive. Similarly, if the function is negative everywhere in the region R, so if f of x comma y is less than 0 for all points x, y in R, then the integral is going to be negative. Another important case is when we can somehow show that the integral is going to be 0. Let's choose a region that's the square from -1 to 1 and -1 to 1. Now consider the integral over this region, this square, of x dA. What's happening with x on this square? Is this function, we have the function f of x comma y equals x, is this function positive everywhere? No, it's definitely not. It's positive over here, but then it's negative over here. But what if we think of this region specifically in terms of horizontal strips? So as I cut the region into horizontal strips, what's happening on a particular strip? Well, over here, x dA has some value, and over here it has the exact opposite value. So along this strip, whatever's happening in a little square over here is exactly counterbalanced by what's happening in a little square over there. And if I add something, if I integrate along a horizontal strip for this function, I can expect that the two halves of the function, the negative part of what's going on and the positive part, exactly balance out. So along every one of these little strips, I have an integral of 0. And then if I'm imagining integrating the whole thing, first I integrate along these little strips, and then I integrate all those sums. But on each of these strips I got a 0, so when I integrate this way I also get a 0. And thus this integral of x over this region, because the function is perfectly balanced, it's an odd function, we end up with a 0. Let's consider another example. Now let the function f of x comma y in the integral be xy. This function is a little bit harder to think about. It's positive some places, it's negative some places. What happens when we try to take this integral? Well, we can use this same reasoning where we go to horizontal strips. So if I go to this particular horizontal strip, y has some fixed value along the entire strip. So I can think of this y as just some constant on that strip. And just as before, there's negative values of x over here and positive ones over here, and they exactly counter each other. So when I add along this strip, I can think of y as a constant that's factoring out, and my x contribution still exactly balanced, so I'm still getting 0 when I add along this strip. If I go to a different strip, okay, well y is a different constant here, but we can still think of it as just being constant along this strip, and the negative values of x and the positive values of x again cancel out when I integrate. So just as before when we just had an x, now when we have an xy, we still, adding up along these horizontal strips, find that on every strip we add to 0, and then we add a bunch of zeros, and so we still have an overall integral of 0. But now for this problem, instead of reasoning via horizontal strips, I could have also reasoned via vertical strips. And that's because along this particular vertical strip, we can think of x as fixed, and then we can think of y as changing with negative values down here and positive values up here, with their contributions exactly countering each other. And so along this vertical strip, again, x is fixed, y exactly balances, and we get 0. And so as we add along every vertical strip, we get 0, and then when we add everything up, we also get a 0. We've just reviewed 3 special, quite useful cases. The first was the case where a function was positive everywhere in a region of interest, in which case we knew the integral would be positive. The second case, a function was negative everywhere in a region of interest, so we knew the integral would be negative. And in the third case, somehow values of the function could be argued to balance with each other as we integrated in different parts of the region, giving us an overall integral of 0.